One of the chief ways you're going to encounter the problem of integration, that is finding the area under a curve, is in the study of probability and statistics, in particular in the study of what are known as density functions. So density functions play an important role in probability and stats, and density functions are designed to help us understand how a particular quantity or characteristic is distributed throughout a population. And through the use of density functions, we can often determine the probability that a particular individual in a population or item in a population, it doesn't have to be a person, possesses a particular characteristic. So in this video, we're going to look at some examples of density functions. So the way density functions are designed, I have kind of a formal definition here of density functions, but we don't really have to study this formal definition. But the way that density functions are designed is that the area under the curve of the density function represents a total population. So again, that might be a population of people, or that might be a population of objects. And density functions always have the property that the total area underneath the curve comes out to be exactly 1. So when you calculate the total area under a curve, that is from negative infinity to infinity for a density function, here we're assuming p is a density function, that area will always turn out to be exactly 1. And then the way we apply density functions is if you find the area under the density function from a particular input A to a second input B. So if this is your lower limit of integration and this is your upper limit integration, that area represents the fraction of the population which also falls between value A and value B. So keep in mind that fraction is going to be between 0 and 1 because the total area underneath the density function is 1. And we often interpret these areas as percentages. So let me give you an example of a density function. Actually, we're going to look at several examples of density functions. And then we're going to look at one of our extra credit problems that I gave you on the extra credit handout sheet, and we'll look at that a little bit more closely so you can get a better idea of how to do those extra credit problems because they involve density functions. Alright, so I've got several examples here, and most of the examples are very intuitive. We're not going to study density functions as carefully as you'll study them in probability and statistics. But I do want to give you the idea of how density functions work and how they're useful. So here's an example I have graphed here of a density function, and what this density function represents, or what the area underneath the density function represents, is the population of patients waiting for a particular doctor. Okay, so in this instance, the area under the curve is this population of patients who are going to see, or who have seen perhaps, this particular doctor. And the quantity that we're interested, or characteristic that we're interested in observing in this population, is the amount of time that they spend waiting in the office for their appointment. Okay, so that's the quantity or the characteristic of the population that the density function is going to help us analyze a little bit better. So we're going to call this density function f of t. I can write that on here just to remind us that this is density function. The input variable here to this density function is the waiting time of these patients for their appointment. Okay, and again, the area under the curve here, this total area under the curve, down to the, in this case, the t-axis, that represents abstractly the total population of the patients. All right, so we're going to start off with a very easy question here. It says evaluate this particular integral. Okay, so that's the area under this curve f from negative infinity to infinity. So that's the total area under the curve f. Well, you really don't have to go from negative infinity to infinity. This curve starts at 0 on the horizontal axis, and notice it goes stops there at 3 on the horizontal axis. So we could have limited our limits of integration here from just 0 to 3. But in any case, all density functions are designed so that the total area under the curve always comes out to be 1. All right? That's a characteristic that's required of density functions. And the reason that area is designed to be 1, or density functions are designed so that this area is 1, is again, this total area underneath the curve represents 100% of some population. So we're thinking of this 1 as corresponding to 100% of the population. In this case, it's a population of patients. All right, so let's see now how we actually apply the density function to answer questions about this population of patients. In this case, we're going to be answering questions about the waiting times for these patients waiting for their appointment. So the very first question is very simple. It's just what's the longest time that anyone waits, and that's quite obvious, right? Because the density function stops here at 3. So that tells us immediately that the longest that any patient is going to wait for their appointment is just 3 hours. Okay. Of course, the least amount of time anyone can wait is 0, right? Okay, so that's why the density function begins at 0. All right, so that's not a very interesting application of the density function. Let's take a look at a more typical application of a density function, which would be something like this. Answering a question like this, what fraction of patients wait less than 1 hour? Okay, so there are the waiting times from 0 to 1 hour. So again, we're interested in how many of these patients, or not how many, but what fraction, what percentage of these patients wait less than 1 hour. So that portion of the population of patients that wait less than 1 hour, that's going to correspond to the area under the curve here from 0 to 1. So if we can figure out what this area is underneath this curve from 0 to 1, just from 0 to 1, that would tell us the fraction of the patients that wait at most 1 hour, or less than 1 hour. All right, so we can see there that looks like maybe a little bit more than half of this total area, right? Okay, is between 0 and 1 here on the horizontal axis. So if we might take a very crude guess here and say, oh, well, maybe it's about half or 50% of the patients wait less than 1 hour. But in this case, we can be a little bit more precise, okay? And let me show you how we can calculate a little bit better, not perfectly, but a little bit better what this total area is here under the curve from 0 to 1. And that's by counting the number of these grid blocks that are contained in this area, okay? These grid blocks are, of course, all rectangles. And if I can figure out the area of each one of these rectangles and then count up the total number of these blocks, the total number of these rectangles, then I get a better estimate for what this area is here between 0 and 1 here under the curve of f. So let's count the number of grid blocks that we have here. There's 1, right? Okay, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 of the grid blocks that are completely contained within the area, these 10 right here. And then I have pieces of 2 or 3 more grid blocks, right, that are part of this area. So if you look carefully here at these little fractional pieces of the grid blocks, it looks like altogether we have about 2 more grid blocks that are part of this area. So I'm going to estimate that this area that I've shaded in here corresponds to the area of 12 of these grid blocks. So if I can figure out what the area of each one of these little rectangles is here, multiply it by 12, then I can determine or get at least a better estimate of what this area here under the curve of this density function f is between 0 and 1. All right, now let's see if we can figure out what the area of each one of these grid blocks is, what the area of each one of these 12 rectangles is. And let's see, it looks like the height of each one of these rectangles, if I read correctly here off of the vertical axis, it looks like the height of each one of these rectangles is 0.1, right? Okay, and I think the width is going to be 1/2 of this distance between 0 and 1, right? Of course, that would be exactly 1/2. So it looks like the height of each one of the grid blocks is 0.1, and the width of each one of the grid blocks, or the length of each one of these grid blocks is 0.5, right? So altogether, I think the area of each grid block would be 0.1 times 0.5, right? Okay, height times length, right? That's how you calculate the area of a rectangle. And then again, in this area we've got covered up approximately, our best guess is about 12 of these grid blocks. So let's take the area of each one of them, which is 0.1 times 0.5, and multiply by 12. Okay, and that will give us an approximation for this area. All right, so 0.1 times 0.12, well, I'm sorry, 0.1 times 0.5, that's going to be about 0.05, and then we multiply that by 12, and so I think that comes out to be about 0.06, right? Okay, or exactly 0.06, and so it looks like that this area here, this total shaded area that I've got drawn in this picture, is about 0.6, okay? And so that tells us then, that gives us then an answer to this question. What fraction of patients wait less than an hour? Well, that's about 0.6, right, times 100% of all the patients, and so that would be 60%. So my initial guess of about 50%, when I was just eyeballing it, looks like that's a little bit inaccurate. It's actually maybe closer to 60%. So about 60% of the total area under this curve is between 0 and 1, or about 60% of the patients would wait less than 1 hour. So you get the idea there, a little bit of how density functions work. Let's try another example. So from this same problem, from this same density function, what fraction of patients wait between 1 and 2 hours? So we're going to go through exactly the same process. What fraction of patients wait between 1 and 2 hours? So that's going to be this area between 1 and 2, right? So again, I can kind of eyeball that and make a rough stab at what that area is, because I know the total area under the curve is 1. But again, we can try counting grid blocks here, and that may give us a little bit better idea of what this area is. So let me see, let's count grid blocks here. I've got covered by this in this region between 1 and 2. So I've got 1, 2, 3, 4, 5, 6. And then it looks like I have probably a 7th one there, right? Okay, I'm missing a little bit of the 7th one, but I have a little chunk up here, right, that I count for part of the 7th one. And then another little piece right there. I don't really have all of, I don't think I really have 8 grid blocks altogether, but it looks like I might have about, 7.5. So let's go with 7.5 as our guess there. So I think we're looking at the area of 7.5 grid blocks, right? And so that's equal to 7.5 times the area of each grid block, which remember we already calculated as 0.05. And so I just take 7.5 times 0.05. Let's do that with the calculator here and see what that is. So that's 7.5 times 0.05, and that looks like about 37.5%, or about 0.375, I should say, which corresponds to about 37.5%. So we're thinking about 37 or 38% of the patients, right, have to wait. Well, it seems like quite a long time. Don't think I'd want to go to this doctor, right? About 37 or 38% of the patients have to wait between 1 and 2 hours to get in to see the doctor at this particular doctor's office. All right, let's try another one here. So this one we're going to do sort of very intuitively, okay? So here we have another density function. This density function is called P of t, and this shows the distribution of the number of years of education. So that's the quantity that we're interested in studying the distribution of, okay, through the population. This density function shows the distribution of the number of years of education completed by adults. So the population here represented under this density function is the population of adults, okay? And this quantity that's graphed along the horizontal axis here is number of years of education. So again, if this is truly a density function, then the total area beneath this curve, has to be exactly 1, okay? Because density functions there are always set up so that the total area beneath the curve is 1. Of course, some portion of the population has very little education, right? Okay, below 8 years of education, so not even an 8th grade education. Some portion of the population has more than 16 years of education. That would be people who actually attend graduate school after they finish their bachelor's degree, right? Okay. And of course, a vast portion of the population here falls right in the middle. That's people who have 12 years of education or a high school diploma. All right, well, let's actually answer that question. Let's estimate the percentage of adults who have completed high school, okay? All right, so what fraction of the population has completed high school? All right, so let's draw a picture of that piece of the population. I think I can draw a really rough picture of that piece of the population because that's going to correspond to the area beneath the curve here above 12, right? So if I shade that in, that's going to be this area here, okay? Now, we don't have these nice grid blocks superimposed on this density function, so I'm not going to be able to get a perfectly accurate estimate of this percentage, right? Okay, But keeping in mind that the total area beneath this curve has to be exactly 1, then I can sort of just guesstimate here, right, what this area must be right here. It looks like it's maybe slightly less than 1/2, right, of the total area beneath the curve. Okay, so I'm going to say I think, oh, this area is maybe about 0.4. Some of you may think it's a little bit more than 0.4. Some of you may think, oh no, it's a little bit less than 0.4, but that's just my estimate. And so I would say that it looks like, at least based on this density function and my best guess here, I think about 40% of adults there have completed high school. Let's try another one. So let's see the percentage of adults who only have a 10th grade education or less. All right, so right here between 8 and 12 on our horizontal axis is going to be 10, right? And so we're interested in what is the area of beneath the curve here from on the left-hand side up to 10, or in other words, this little piece of area. And so again, I don't know exactly, not going to be able to get a great estimate for what that area is, but just keeping in mind that the total area beneath this curve is exactly 1, I can use that knowledge to at least give a rough ballpark figure of what this area is here from on the left-hand side under this density function curve. And so I'm thinking that looks like it's about 1/4 maybe of the total area beneath the curve. And since 1/4 of this, and since this total area beneath the curve is 1, then maybe 1/4 of this would be about 0.25. Okay, so you may say, no, I think it's a little bit less than that, Dr. Waller. Other people say, no, I think it's a little bit more than that. But I'm going with about 0.25, which tells us that about 25% of the population has less than a 10th grade education. Another way now of applying our knowledge here of this portion of the population that has less than a 10th grade education would be to answer a probability question. So you might say, you might ask, if we pick a person at random, totally at random, an adult totally at random, what's the probability that we pick someone who has less than a 10th grade education? And the answer would be, well, that probability is 25%, or about 1 in 4, right? Okay, if we just go into the population and choose a person at random, we have about a 25% chance, right, that we'll pick someone in this portion of the population, since about 25% of the population falls in to this portion, right? Okay, so we can also use density questions, density functions, right, to answer probability types of questions. And that's why density functions have such an important role in probability and statistics. Let's try another example. Here's a density function called S. This one's kind of interesting because in this case our population is not a population of persons. It's not even a population of objects, actually. Okay, what the total area underneath this curve represents is 100% of the Earth's surface. Okay, and what the characteristic that we're interested in observing for the Earth's surface is its elevation above or below sea level. Okay, so positive elevation there means portions of the Earth's surface that are above sea level, 0 corresponding to exactly sea level, and then portions in the negative here, elevations, correspond to portions of the Earth's surface that are below sea level. Okay? So here, the area beneath the density function represents the total surface of the Earth. So let's see if we can answer a question here now about the Earth's surface. It says, approximately what fraction of the Earth's surface is below sea level? Okay, so you may know the answer to this question because this frequently comes up in geography classes. We know it's a big fraction, right, of the Earth's surface is below sea level. Let's see if we can get an approximate value from this density function. And then you can look that up with Google and see how close we got to actually being correct, right? All right, so again, 0 corresponds exactly to sea level. And so we're interested in what is the area here below sea level? What's the area beneath this density function over here on the left-hand side of the horizontal axis? So again, we don't have a grid on this axis superimposed, so we're not going to be able to get a super accurate estimate, right? Okay, but we can at least get a decent estimate by keeping in mind that the total area here beneath this density function is 1, exactly 1. That's the way density functions are designed. So keeping in mind that the total area here beneath this curve is 1, we look at the shaded area and we can make an estimate for how much of that total area of 1 is in this shaded portion. So what does that look like to you guys? I'm thinking, oh, that's about 70%, right, of this total area is in the shaded portion. So 70% of 1 would be, of course, 0.7, right? And that gives us at least a rough answer to this question, right? We're thinking 70% of the Earth's surface is below sea level. And again, another way to express this idea is if you randomly chose a position on the surface of the Earth, right? Okay, just randomly picked out a position on the surface of the Earth, what would be the probability that it's below sea level? Okay, so what's the probability that you would pick a position at sea? And that would be, you'd have about a 70% chance, right, that if you randomly picked a position on the surface of the Earth, you would pick a position that was below sea level. I think I've got one more example here. So this density function, which we're calling g of x, that's an x there, this represents the distribution of GPAs among students at Faber College. You can look up on Google and see why I chose Faber College. That's a famous fictional college from the movies. Okay. So the area here beneath this particular density function, again, that area is 1, but this area represents the population of students at Faber College, and what the characteristic that we're interested in observing for that population, of course, is their GPAs. They've got this curve, this density function, drawn a little bit accurately. It should come down all the way to the horizontal axis, right, all the way down to the x-axis right here at 0, because I don't think you're going to have a GPA below 0, okay? If you have a GPA below 0, then you're really in trouble. And of course, the maximum GPA you can have here, at least at Faber College, the way GPAs are calculated is in the standard way. The maximum GPA there apparently is 4. So we want to answer here roughly what fraction of students are on probation at Faber College, what fraction of students would have a GPA at most 2. Okay, that's usually what puts you on probation at most schools, is if you have a GPA below 2. So in other words, we're interested in knowing what fraction of the students here falls into this portion of the population. Okay. So again, we'll just have to get a rough estimate for this. We know the total area beneath this density, this GPA density curve is 1 because it represents 100% of students. So we are looking at this area, and I'm saying that that is about, does that look like as much as a third to you? I don't think so. Maybe, well, maybe it is a third. Okay. So I'm going to go with a third there, or about 30%. So I think the area here from 0 to 2 is about 0.3, which tells us that about 30% of Faber College students are on probation. And again, that's a very rough estimate. You may have a slightly different idea for what the area of this shaded region is. Let's see, roughly what fraction have honor grades? So I think honor grades would be above 3. So at least that's how I'm interpreting honor grades. So let's see, we're trying to get an idea of what's the area of this little piece over on the far right. GPAs between 3 and 4. That looks actually probably pretty close also to a third, but I'm thinking maybe a little bit less than that. Maybe this area altogether is about 0.2. And again, you may think it's a little bit more or a little bit less than that. Again, I'm just having to eyeball it because all I know is that the total area beneath this density function is 1. So I'm thinking this must be about a fifth of 1, or about 0.2. So I'm going to go with, as my estimate, about 20% of students at Faber College have honor grades. So that gives you a rough idea of how density functions are used. Let's look now at a case where we can actually calculate the area beneath the density function a little bit more accurately. And this is by looking at your extra credit homework assignment, okay? Because in the extra credit homework assignment, here it is, okay, I actually have the formula for the density function, and it's already been coded into Desmos for you. So you can use rectangular approximations like we've been using to approximate areas under curves to get a very accurate estimate for areas beneath this particular density function. So this is a density function. I'm calling it f of x, and what this the area beneath this particular density function represents is a population of adults, okay? And we can think of this as, say, adults in the United States. And the quantity or the characteristic that we're interested in studying for this population of adults, so that's the values that are plotted here along the x-axis, these are their IQs, their intelligence quotients. And notice that this density function has a very symmetric shape. This is a very famous type of density function known as a bell curve, okay? And often when you observe the IQs of a population of adults, you will get a distribution of those IQs following such a bell curve, okay? So this is actually a very famous and controversial type of example. Not controversial in the sense that the density function has this shape, but controversy about what IQ actually measures, right? But nevertheless, okay, here's a density function for the IQs of a set of a population of adults. All right, so what we want to do here is to estimate this area, okay? So we want to estimate the area between 80 and 120. So the area beneath this density function from 80 up to 120, okay? Now keep in mind the total area. I'm going to have a hard time shading this now because this is kind of a big area here beneath this. Again, this is called a bell curve, this type of density function. Right? So we know that the total area beneath this density function has to be exactly 1, right? But we want to know how much of that area of 1 falls between 80 and 120. So it looks like it's a very large piece of the area, right? Okay, we're going to have an area here very close to 1, but not exactly 1, because there is a little bit of the population with IQ between 70 and 80, and then a little bit of the population over here with IQ, or well, actually up to 80, and then there's a little bit of the population here with IQ above 120, right? Okay, but it looks like a substantial portion of the population is going to have IQ between 80 and 120. All right, so we're going to use Desmos here actually to estimate this area. Okay, so remember in Desmos we have a tool there that will allow us to fill up this area with rectangles. Okay, and then sum together the area of the rectangles, and by using more and more rectangles, we can get a very accurate estimate for what this area actually will turn out to be. So what I want you to do in this extra credit problem is to complete this table where we're going to approximate this area by using rectangles, okay, starting with 4 rectangles and then going all the way up to 10,000 rectangles, and then use this table to get an estimate, right, for what this area is underneath this density function between 80 and 120. All right, so you can now find the link to the Desmos tool you're going to use specifically for this density function at this particular URL. Because I've already got this set up for you, but you don't have to type in this URL. Actually, if you go to WebAssign, there is, on the announcements, there is a link to this web address, okay? So you can just click on that link and it will take you directly to Desmos and this particular tool that I'm getting ready to show you, okay? So let's see if we can get Google Chrome here now to respond. There it is. Oops, I think it's coming. I had it open earlier, but let's see if we can get it back again. I may have to reopen it. Ah, here it comes. Ah, there it is. All right, so here's the tool in Desmos that we're actually going to use to fill up this area between 80 and 120 with these vertical rectangles, right? Okay, so we can estimate this area quite accurately by choosing more and more rectangles. So I've already got the formula for this density function typed in. Notice it's a nice complicated formula, but you don't have to learn that formula. It's already typed in there for you, okay? And we want to find the area between 80 and 120, so that's already been typed in, and then we're going to use more and more rectangles here to get an approximation for this area. So I've started with 4 rectangles, so that would be filling up Desmos with 4 rectangles. So if I drew a well, I can't draw a picture of this on here, but you can sort of visualize what the rectangles would look like, right? Okay, 4 of them between 80 and 120, and right there, okay, in slot number 10, right? There is, with 4 rectangles, our approximation for this area. It's about 0.9368. So let's go back to our sheet here and fill that in, okay? So if we only use 4 rectangles to approximate this area, only 4 rectangles to approximate this area, we get that the area is already 0.9368, meaning that over 93%, right, of the population is going to have an IQ between 80 and 120, okay? But that may not be a very accurate estimate because I only used 4 rectangles to estimate that area. So let's increase now the number of rectangles. Okay, so let's go back to Desmos and change that number of rectangles. That's in this box number 8. So let's change that number of rectangles. If I can get my, there it is. Okay, so let's change that. Let's change that number of rectangles. If I can get this son of a gun to respond to me here. That's going very slow. Alright, let me open it again. There it is. So let's change that number of rectangles now to 10. Okay, so when we increase the number of rectangles to, that's 0, so that's not the right number of rectangles. So when we increase that number of rectangles to 10, then notice that gives us a little bit better estimate for the area. Now it looks like it's about 0.9516. So let's go fill that in our sheet there, right? Okay. And now we can see that actually it's closer to 95% of the population has IQ between 80 and 120. Okay. All right, let's increase this again. So let's go up to, let's increase this again. So let's go up to 20 rectangles. And see, notice 20 rectangles doesn't give us a much better approximation than 10 rectangles. Now it looks like to 4 decimal places about 0.9538 is the area underneath this curve between 80 and 120. Let's fill in one more value here, and then I'll let you continue. Let's go up to, what's the next one that we want here? Let's try 50 rectangles. So let's go up to 50 rectangles. So let me put 50 in there for the number of rectangles. And notice now we're not getting a much better estimate. Now to 4 decimal places, it's about 0.9544. So very clearly, right, you can see that as we are increasing the number of rectangles, we're getting a progressively better estimate for this area beneath this curve between 80 and 120, but not after 50 rectangles, right? Our approximation is not changing all that much. So I'm going to let you continue here to fill in more and more rectangles. I want you to go all the way up to 10,000 and see what estimate you get at 10,000 rectangles, and you'll see that eventually adding more rectangles is not going to change your estimate very much. Okay, and then you can use that as your estimate for the area beneath this density function from 80 to 120 to 80 to 120. All right, now how would we use that? Okay, well, of course, we use that estimate exactly the way we did in the previous examples. So a person with an IQ between 80 and 120 is considered to have normal intelligence. So we want to know what percentage of the population has normal intelligence, and that's how you can use your area estimate, right, to give a value or an estimated value for this percentage of the population that has normal intelligence. We just want you to round to a couple of decimal places. We can already see probably, right, rounding to a couple of decimal places looks like it's going to be around 95%, right, because we can already tell that about 0.95 that fraction of the population, right, is going to fall between 80 and 120 beneath this curve. So there are some other questions that we're asking here about this bell curve, this IQ bell curve. So I'll let you try to answer those questions. And then also on this sheet we have another density function that we want you to answer questions about, okay? And you go about answering these questions very similar to that problem number 1. And again, this one is already set up for you. The formula for this curve is already typed into Desmos, so you don't have to worry about typing in that formula. All you do is have to go to this URL in Desmos, and it will bring up this density curve for you. And you can find a link to that web address right in WebAssign on the announcements page. Okay, I'll show you what that is going to look like actually when you call it up. So there, well, that's not it. Let's try again. There it is. Okay. So let's open this graph. There it is. Okay. So there's that second density function that we're going to be using in problem number 2. This has to do, I think, with the amount of time it takes to recover, the number of weeks that it takes to recover from a particular infectious disease. Okay, so there's our brief lecture there about density functions. And again, this is probably how you're going to encounter frequently this problem of integration or finding the area beneath the curve in practice. There are lots more applications of integration, I should point out, other than just density functions, but this is the one I think you may see most frequently.